All right. So today, guys, sorry I'm not there, and I'm really sorry. My understanding is I had some trouble effectively posting the safety stuff, and God, I'm sorry about that. I've been um, I've been hotspotting and using the hotel Wi-Fi here, which just keeps kind of coming in and cutting out and coming in and cutting out, and I guess at first things didn't post at all. Like they were in, but when I pressed publish, they didn't publish. And then somebody said they published twice and they saw things doubled. Sorry. Really am sorry. This is why, mostly do things on paper now. Anyway, today's lesson, which I hope works out okay for you, um, is going to be a fairly quick one. And I normally start this lesson with a lab. Um, in fact, I normally start this lesson with a poem. Um, yeah, if I'm being honest, if I'm telling you the truth, I usually break out my Walt Whitman um, and read a poem called "When I Heard the Learned Astronomer." When I heard the learned astronomer, when the proofs, the figures were ranged in columns before me, when I was shown the charts and diagrams to add, divide, and measure them, when I, sitting, heard the astronomer where he lectured with much applause in the lecture room, how soon unaccountable I became, tired and sick, till rising and gliding out I wandered off by myself in the mystic moist night air, and from time to time looked up in perfect silence at the stars. And I love that poem, uh, in part because it's a reminder to, not forget the beauty, not forget the delight that sort of as we learn about the universe around us, especially as a science teacher, I take great joy in learning about how things work and the numbers and the figures and the equations, but to not forget from time to time to just look in wonder at the universe around us and how it works. And at the same time, I think too about looking up at the stars as being maybe the most fundamental thing in learning about science. It might be the most basic thing. You imagine ancient peoples looking up to the stars and asking what they are, and asking about where our place in the heavens and where our place in the universe is. But today we're going to learn about how looking at light really became the great insight to how it is that stuff works, which might seem strange on the face of it. If you study the quantum model, which is really what this unit is about, of chemistry, the quantum model of matter, what's really interesting is that it is light that provided for us all of the great insights in how the atom actually works. So if you remember from our last lesson, we talked about kind of the really quick history of the discovery of the atom. And I'll just, throw that up here and we can quickly take a look. Right, so we said the atom sort of starts as this thought experiment. If we divide down and divide down and divide down, do we eventually get, as we cut pieces of matter in half, to something that which is indivisible, something we can't cut in half? And Democritus theorizes that this thing must exist, and he calls it the atom. But that's just that. It's a thought experiment. It's an idea. It's a possibility. Um, and then from there we get John Dalton, and Dalton is the first one who says that perhaps this is true, but does so based on some evidence. I'm not quite sure why these things are out of line. That's better. So for Dalton, he looks at the electrolysis of water and at the fact that when you break water up, no matter what you do, you always seem to get twice as many pieces of hydrogen as you do pieces of oxygen, which is to say you get twice as much volume of hydrogen as you do of oxygen. But even more interestingly, even though there's twice as much hydrogen, that oxygen seems to weigh 16 times as much. And so he starts to build back the idea that water must be made of particles, and one of those particles is called oxygen, and one of those particles is called hydrogen. And in fact, it works if it's made of two of the little hydrogen pieces and one of the little oxygen pieces. Excuse me. And then years later, J.J. Thomson gets to knocking little pieces inside of an atom off and figures out that Well, if those little pieces can come from inside the atom must be made of little pieces, must be made of more than one particle put together. And if those little light ones have a negative charge, the rest of it must have a positive charge for the thing to be neutral overall. And so we get the discovery of the electron. And then Rutherford's students shoot particles through gold foil. And what they expect is that the shooting of those particles through the gold foil will cause minimal deflections because they should be able to just break through. And what they find is that normally they make no deflection at all, as if they're passing through pure empty space. And once in a while they bounce off as if they're hitting something very heavy and very dense. And what he concludes is that the atom must be mostly empty space, but that inside of that, there must be this really dense portion where all the positive mass is. And so we get to this built-up model of the atom, right? And so now we get to here. So we're going to talk about the Bohr model of the atom. And normally, at the beginning of this lesson, like I said, after I had finished reading you a poem, we'd do a little experiment. And we will do this, I promise, on Monday. We'll take a look at it. But we would go back to the back of the room, and I would break out what I like to call the Deathtron 6800. And we would take a look at that. So what I want to do now is, I want to talk about that. So let's take a look. And I want to kind of put myself in narrating position here. Let's see if I can do that. Whoa. Okay, there we go. So, and I wonder, can I crop myself off here? Sorry, I'm just, can I add a crop? Oh, crop. Aha. Whoa. Okay, there we go. All right, there I am. Look at me. Okay, so we're going to try and keep that going for the duration of this thing. So you can stare at my ugly mug while also watching the video here. So, with that in mind, what I want to do is just show you the experiment we'd normally do. So normally I would break out these glass tubes, and these glass tubes are full of individual gases. And I'm just going to let them play. But this tube is full of hydrogen, and if you put an electric signal through it, if you put very high voltage electricity through it, it will glow. And it will glow in this particular color that you see here. And if we take that same electric current and we put it through helium, it will glow. And it glows a different color. And if we take that same electric signal and run it through neon, it glows a different color. And likewise, if we take that same electric current and run it through nitrogen, it glows a different color. And you might say, okay, who cares? But then what we can do is we can put this light through a prism, or what we call a piece of diffraction grating. And what we can do when we do that is we can see that this light is actually made up of 2 or 3 or distinct wavelengths of light. And if you look there, that's what a prism does. Remember, so if you can see here in this video, you're getting a full rainbow of light, and that full rainbow of light that you're seeing there is actually from the light in the room, right? So that's just kind of the light there. But that particular glowing light that we have over there, the neon tube, is actually just these 4 distinct wavelengths of light. And if you were in a perfectly pitch black room, that's all you'd see, is you'd see those 4 distinct wavelengths of light. And he's showing here that if you have a ruler, you can actually measure them. And we'd look at that. Now, I don't want to make too big a deal of this, except to say that this ends up being really important. and then we'd talk about why. All right, so we'd do that experiment, and we'd look and we'd say, oh, wow, when you shine a light by putting a ton of electricity through an atom, it makes light, and it makes light of really specific wavelengths. And what does that mean? So let's talk about what that means. Again, I'm just going to see if I can get my angle here so I can write. Yeah, okay, that should be all right. So what we have is the idea of this. We have that our model of the atom looks like this. We have protons, and we have neutrons, and they live in the nucleus, right? Just like that. And then around the nucleus, we have these orbitals, right? And in the orbitals, we have the negatively charged electrons, right? And they orbit around. Okay. And the question raised by this is, why don't the electrons orbits change? I.e., why not spiral into the nucleus or away? For example, our moon right now orbits the Earth, but its orbit is actually ever getting a little bit bigger. And with every single revolution, ever so measurably, it gets farther away. In fact, if you'd been on the Earth millions of years ago, at night the moon would be much, 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 much bigger in the sky than it is today. And if you were to live to, to be another billion years old, the moon would look much smaller in the sky. It's going to get much further away. Its orbit isn't perfectly stable. Well, electrons orbit very, very quickly, but their orbits, their radii, in other words, the distance they orbit, is fixed. And this raises the question, well, why? How do we know that? And this is where the experiment that we looked at, this idea of looking and saying, okay, well, oh, no, not there. That's just me. Where is it? No, not there. Yeah, this experiment here, and seeing these spectral lines, which may just look like a pretty trick, it may just look like pretty little pieces of color, actually becomes very, very, very important. Because Niels Bohr used the emissions of light by hydrogen under high voltage to explain electron orbits. And his idea leads to what we call the quantum theory. I should say, his discovery was the quantum theory. Okay. Specifically, what it basically says is that quantized energy states solve the problem of orbital stability. So you might rightly be asking now, what the heck does that mean? So let's talk about what the heck that means. So let's take a look at Niels Bohr. This snappily dressed little fella here is Niels Bohr. And we'll just say what we would have shown in that little experiment, which is that when a voltage is applied across a gas, it emits light. Of very specific wavelengths. You can think neon bulbs. And we're going to say of very specific wavelengths. But we're going to remind ourselves that the wavelength of light tells you its energy level. We see it as color. Different color light is how our eyes interpret light of different wavelengths. But that really means we're looking at light of different colors. Or, sorry, that's what we see. What that really means is we're looking at light of different energy levels. So the energy level of light and it's seen as color. So red is a specific energy level of light. Blue is a specific energy level of light. Green. And each color of the rainbow is light of different wavelengths. And what makes light have different wavelengths is that it has different levels of energy. So how does this light get made? Well, it turns out that this light, the light you get from a gas by putting electricity through it, is made by electrons moving in their orbits. I shouldn't even say that, actually. That's by electrons changing orbits. So to maintain orbit requires a certain amount of energy. That's true for anything in orbit. If you want to put a ship in orbit, you have to give it a certain amount of energy, and it has to maintain that amount of energy to stay in orbit. And if you want to go to a higher orbit, you have to put energy in. So if a ship wants to go to a higher orbit in space, it has to fire a rocket and go up. And if you want to go to a lower orbit, you actually have to get rid of that energy. So for example, when a ship wants to leave orbit and come back to Earth, it has to get rid of all that energy. And usually the way it does it is by getting really, really, really hot. We call that friction against the atmosphere. But if it didn't do that, it would do it by going really, really fast, which would be a problem if you're trying to land a ship. But if orbit levels change, energy levels have to change. And there's no way around that. Physics tells us that. So the reason we actually get light emitted is because light is just an electromagnetic wave. All that a light is a change in the electromagnetic field. If you shake an electron in one place, it will produce electrons shaking down the way, and it makes a wave that does that. So what happens is this. If we put electrical energy through hydrogen normally has one proton and no neutrons in its nucleus. All right? And then in its orbit, it has only one lonely little electron. And here is that lonely little electron right there, and it's orbiting along there. All right? And what's going to happen is we're going to blast this with energy. In this case, high voltage electricity. And when we blast it with energy, when we blast it with high voltage electricity, sorry, OneNote crashing, does that every once in a while. What's going to happen is that electron is going to absorb that energy, and because it absorbed that energy, it's going to move out to a higher orbit, because that's what an electron with more energy does. It's going to move faster, and to move faster, it has to be in a bigger orbit. So what would happen is that electron is now going to leave that normal first orbital that it would be in, and it's actually going to go up to a higher orbital. That's the electron. Whoa. Is going to move to a higher orbital, moves to a higher energy limit. And it does this using the energy it got. And then what's going to happen, and I wish I'd left a little more room to the right, so I'm going to highlight these and move these, and if you need a bit more space, you can do the same. What happens is that what goes up must come down. That electron's actually going to go back to its regular orbit eventually. All right, it's going to go back. There's going to be, all the forces in the nucleus. The reason it was in that first orbit to begin with, it's going to make its way back down there. It's going to fall back down to its first orbit. And as it falls back down to that first orbit, it had to move back down here from the second orbit. And as it moves down there, it's going to release energy. And it releases energy in the form of light. Okay, so we're going to say it releases the same amount of energy it absorbed as light. As a photon, as a ray of light. And we can say the energy of the light ray is the difference in energy between the two orbital levels. Now, if this all sounds a little confusing, that's because this is confusing. It really is. But basically what we're saying is, if you take an electron, all right, so we have the nucleus here, and then we have two orbitals. If you take an electron and you put it up to this orbit, and then it falls back down to that orbit, it will release a ray of light that has the energy equivalent of the difference between these two orbits. All right? That is the amount of energy that will be in the ray of light. All right. Now, again, this isn't yet the complete part of Bohr's theory. Okay, so this explains why we get light when we shine energy, when we put a bunch of energy through a hydrogen gas. But now here's where Bohr makes his observation. There's only very specific rays of light that are visible. And in fact, when we actually do this experiment, I will take a photo of our emissions that we get on our camera, and I will paste it right under this, and you'll see that they line right up. I have a version of this lesson that I taught a couple of years ago, and I'm going to pull it up just to show you that it really works, that I used my cell phone camera. I'm just going to check and make sure I'm still in here. Oh yeah, there I am. Look at me. I used my cell phone camera, and you'll see that these actually lined up just perfectly. Where's the last time I taught this course? There we are. Yeah, so if you look, I shot this with my cell phone camera, and if you look and see, you'll see that we got the rays of light to just match exactly what they were supposed to equal, right? We got a ray of light right there, and a ray of light right there, and a ray of light right there, and you can barely see it, but there's one there as well. And that was just done with a cell phone camera shining through a little prism, shining through a little piece of diffraction grating. But again, what we're seeing here is that the energy levels released this way are very specific. All right? In this case, there's 1, 2, 3, 4 arrangements, which really means 4 wavelengths of light four different paths the electrons could have taken. You can see one of them is lower energy and a higher energy one, and then 2 really high energy ones. But there's just 4 different paths. So what makes this occur? Well, what makes this occur, just what we set up below, is that the electron has an orbit it normally sits in. It jumps up to a higher energy level, and then when it jumps back down, it releases it as light. You don't need to know this equation. Don't worry about that. But what you do need to know is that what it's telling you here is that the change of energy determines the frequency of the light produced. Now, Bohr shows us something more than just that, though. Bohr shows that since only specific wavelengths are possible, two things. One, only certain orbital distances are possible. In other words, if when we do this, we always get the exact same energy being released and come back, and how much energy is released and comes back depends on where the orbits were, then if there's only specific energies of light allowed, then there must have only been specific orbitals of the electrons allowed. So he says that this must mean that electrons aren't moving randomly around the nucleus. They are moving in orbits such that they always have a really specific amount of energy. They have specific orbital energies Because again, if they could be at any random distance, any random energy level above the nucleus, then when you gave them more energy and had them fall back to where they were, they would have random amounts of light put through them, right? Because the thing that you discover is if you change the voltage going into the light, into the hydrogen, it might change how much light you get, but it never changes the energy of the light. No matter what, the math tells us the electrons are going from one orbital up to another orbital and then back, and that those orbitals always seem to be the same for any hydrogen anywhere. And that means that the electrons in any hydrogen anywhere can only exist at certain orbital distances. So that's good. But then it tells us something else too. He also learns from this that the electrons don't move between them. Changes are instant and total. Now, this is weird. This gets into where science starts to feel like science fiction, where we start to think like transporter. But Niels Bohr's math tells us that if the electron moved up to the higher orbit and then fell back down to the first orbit, what you would get is a light photon that changed up to a certain frequency as that move, because the first little move would give us just a little bit of light and frequency, and it would build up in frequency as it went. But instead, you get these discrete, perfectly clear lines of exact amounts of energy, which tells us that the fall isn't gradual. The fall has to be immediate. In other words, the electron doesn't move from this orbit up to that orbit. It's in this orbit, and when you give it more energy, it is now in this orbit. And there's nothing in between. And this is what we call quantization, which means there's only specific amounts of energy allowed. So if the distance of their orbit from the nucleus determines how much energy they have, then they are allowed to be in certain orbits, and they're not allowed to be between them, which means they can't move from one orbit to another, because then for a while they would be between them, which means they simply have to change from one orbit to another, which means they have to immediately stop being this orbit and start being in that other orbit. Now, for us, on a conceptual level, this does not make sense. It is really confusing. But the math tells us that that's what has to be happening. And this math has been confirmed over and over and over again. But this is what we call the quantum model of the atom. And it fundamentally breaks the way we think about nature and the way we think about matter working. So if that seems complicated, well, it is. It actually is very complicated. But what we're going to do is we're just going to go nice and slowly with this idea. So over the next bunch of days, we're going to talk about the implications of the fact that atoms can only exist in certain orbits. But we're going to start just by describing this. And we're going to say that where the Bohr model of the atom starts to work is that if we take something like, let's not take hydrogen, because that's boring. Let's take something that has a few more protons and neutrons. So I'm going to say we have 11 protons and 12 neutrons. I'll let you decide what element that is. I have faith in you. But if we look that up on the periodic table, we're going to see if it has 11 protons, it must have 11 electrons. And if we look, we know from the periodic table that Bohr is going to eventually find that that first shell can only hold 2 electrons. The second one can only hold 8 more, so that would bring us up to 10. So to have 11 electrons, we're going to need 3 shells. There we are. I'm not happy with how those went shape-wise. Better. Okay, so we would have 2 electrons in the first shell. And we would have 8 in the second shell. 1, 2. Oh, that's not the second shell. That was still the first shell. 1, 2, 3, 4, 5, 6, 7, 8. And we would have just 1 electron in the outer shell. There we go. Well, when we describe these electrons, what shell they're in is a measure of how much energy they have. So this electron here is relatively a high energy orbital compared to that one there, or that one there. All right? It has more. And so we want to be able to describe this. So how we describe it is this. We say that this electron has a principal quantum number, which we call n equal to, well, it's in the third orbital, so equal to 3. Its principal quantum number tells us what orbital it's in. So, what about this electron here? Well, its principal quantum number would be n equals 1. And for this electron here, its principal quantum number would be n equals 2. And the principal quantum number tells us which orbital the electron is in. What Bohr discovers, and what other scientists discover going on, is that that number isn't just descriptive. It's not just like, oh, the first, the second, the third, but it will actually end up being involved in a lot of the math that determines how these electrons behave. You can actually build equations that describe the behavior of electrons, how they function, and when you do that, this number becomes very important. Knowing which orbital it is in will describe its behavior. So, for example, there's an equation by which you can calculate what wavelengths of light you will get when you excite electrons and then let them fall back to their ground state. And if you want to do that math, we'll do a bit of that, though not too much, but you need to use this number. It comes into effect. So knowing what orbital the electron is leaving and what orbital it's going to, say we excite this as so much, we give enough energy to go up into the 4th orbital, and then to go back down, well, we could do some math that's going to tell us the wavelength. And that number, that principal quantum number, is going to come into effect. Now, it's not the only number that's going to come into effect. We're going to do that for this. I'm going to give you a little bit of homework. It really is very little. This is trivial. It won't take you long. But your homework is to draw Bohr-Rutherford diagrams. We're going to remember how to do that. For any 3 elements, I don't care which you pick, and identify the principal quantum number for each of their electrons. The easiest way to do that would probably just be to use a highlighter. I have lots of highlighters in the room, so you're, of course, welcome to use that. So, for example, on this one we just did, if I decided that any electron that had a... Oh, geez, golly, gee gosh. If I decided that any electron that had a principal quantum number of 1, I was going to highlight in blue. That would be these 2. And if all the ones that had a principal quantum number of 2 I was highlighting in yellow, that would be all of those. Oh, and these, of course. And any that had a principal quantum number of 3, if I was going to highlight them in pink, that would just be that one because there's only one there. So we just want to make sure we understand that we know the n value, we know the principal quantum number of an electron by looking at where it's located in the element. All right, this lesson probably feels a little bit esoteric, which is to say, it probably feels a little bit, oh my, it probably feels a little bit confusing, right? A little bit like, what are we talking about here? All I can say is, bear with me, and just try to make sure you follow along and pay attention. In the end, the theory isn't going to be as important in this course as what we do with it, but if you can understand the theory, that's great. The basic theory today, the long and the short of it is that Niels Bohr tells us that what orbital an electron's in, how far it is from the nucleus, the shape of its orbit, is determined by how much energy that electron has. And what happens anytime we move electrons, and there's a lot of ways we move electrons, but this example where we zap them with a bunch of electricity, they jump up, and then they jump back down, and as a result they release light. Whenever we move electrons, they can't move just anywhere. There's only very specific distances from the nucleus they can be. There's only very specific amounts of energy they can have. And this is called quantization. It means that they can have this much energy, or they can have this much energy, but nothing between those two amounts. They can either have this much, or that much, or that much, but nothing in the middle. And when we say nothing in the middle, we don't mean that you can move between them, but then you're going to stop there. It literally means that you can't move between them. That if you want to take an electron and move it from having this much energy to having that much energy, that change happens instantaneously. It literally means that the implication of that is electrons must simply be able to change position without moving between those two positions instantaneously. And that seems to break our understanding of the universe, but the math tells us it has to be true, and the math has been confirmed over and over again. And this becomes the foundation of what we call the quantum model of the atom. And everything we do with more advanced chemistry begins to depend on this quantum model of the atom. So take that for what it is. We're going to carry the quantum model on in our next lesson. We'll actually also do that experiment and take a look at it. And I apologize once more for any and all mix-ups with the online stuff. As you know, I struggle sometimes with technology, as I guess we all do. All right, have a wonderful day. Well, I will see you all on Monday. Have a wonderful weekend. Get that little bit of homework done. 3 Bohr-Rutherford diagrams. Identify the principal quantum number of every electron involved. Ciao. See you. Bye. And make sure your safety stuff's done. I know I was late, but that doesn't mean you can be.